So our last example in this lesson, we're going to look at a particular linear transformation and try and answer a bunch of questions about it. We're going to find A such that t of x is equal to A times x, which is really just a fancy way of saying we want to find the matrix of transformation, describe the null space and the range of t, and give the rank and nullity of t. So the first things first, we'll get that matrix of transformation because that is going to tell us all the other information. And we can find the matrix of transformation again by looking at the coefficient matrix that is made up of the coefficients off of our transformation. So that would be 1, minus 1, 1, 1, and 0, 1. So there's A. And now we want to find some more information. So we need the null space and the range of t, and then of course from that we can then determine the rank and the nullity of t. So let's go after the null space of t. So remember, the null space is the set of all x's such that A times x is equal to the 0 vector. That means for us we go ahead and put this into an augmented matrix. And we can row ref it. So we do that. And the result is 1, 0, 0, 0, 1, 0. And our column of zeros on the end. Since this has only the trivial solution, the null space of t is equal to the 0 vector only. So let's write that out. So that is the only vector in the null space, and therefore the nullity in this case is actually 0, is the way that we describe that. So now let's do the range. So R of t, which is equal to R of A, which is really just the range of the matrix of transformation, so our normal context of range. And what we want to solve then is for the set of all x's that are equal to some particular output b. You'll remember that this is how we determined the range prior. So we have, again, using our alternate definition for what the transformation is, it's A times x equals b. So now it looks familiar. We'll throw that into an augmented matrix, and we would get 1, 1, 0, minus 1, 1, 1, and b1, b2, b3, representing our values in our range. And as we've typically done, we would put this into a row-reduced echelon form, and I'll tell you what we get there. So we get our 1, 0, 0, 0, 1, 0, and for the other side of the equation, we get b1 plus b3 for the first element, b3 for the second element, and minus 2b3 plus b2 minus b1 for the last element. Of course, that's the most important one because that's going to determine our consistent relationship. So this is consistent if and only if minus 2b3 plus b2 minus b1 equals 0. And that implies that b3 equals 1/2 b1 minus 1/2 b2. Then we can write out our range of our transformation as b1 equals b1, b2 equals b2, And then B3 is going to be equal to 1/2 B1 minus 1/2 B2, which we can then write out in a vector form, which would look like B1 times the vector 1, 0, 1/2 plus B2 times the vector 0, 1, negative 1/2. And that's a nice description for our range of t. Then we clearly have our two basis vectors here. And if we wanted to make those look a little nicer, we could take a multiple of those by multiplying each of them by 2 to get back to some whole numbers. So our basis here for the range of t is 2, 0, 1, and the other one would be 0, 2, minus 1 then, for a nice set of basis vectors. We have two vectors in the basis, so the rank then is equal to 2. So now we've answered that question as well. So just some notes that I want to make here as we went through this. So here when we were looking for the range of A, if we remember that the range of A is equal to the column space, then we can also find a basis here by going RREF of A transpose transpose. So that's a reminder that we have an alternate definition for the range, again, as the column space. And also we can sort of clean up our work a little bit here. If we think about the range as a special case of the null space, then if we do this first, then we can take B1 equal to 0 and B2 equal to 0 and B3 equal to 0, and we can determine the null space from that. So it's just a little bit of an efficiency thing from that perspective. And the last thing I'll point out here then is that we noted that the dimension here was equal to 2, so the dimension of the range was equal to 2, which in that case implies, given our scenario, that the null space of T had a nullity or dimension 0, again, based on our specific scenario. So that just confirms that the dimension of the null space should be equal to 0, which is what we also already found. So we get a nice little confirmation on that as well.